All right, everyone. Welcome to the afternoon session. I'm delighted that Peter Bürgisser will be telling us about upper bounds for matrix multiplication.
Okay. So hello, everybody. It's my pleasure to be here and explain. My task is to explain about laser method, and that's not so easy. So in the first talk, let me recall some of the algebra, tensor algebra, when we deal with tensors. So it's about tensor algebra. So I hope this is readable. So partly I will recall what we already learned in JM's talk, but I have my own notation, so let me go quickly through that. So, okay, we all know what is a tensor, but it's good to write it. So in order to fix notation, you can think of it as a three-dimensional matrix. It's over some field F. Dimension parameters are M, N, and P. Or in a more invariant way, you can view this as a tensor product of three vector spaces, obviously. It's an element here. OK, so let's say you have another tensor T prime. I want to define what it means that they are isomorphic. So let's say this is here. So there is a couple of definitions. So what is isomorphism? So I denote it this way, and this means the following. So I get linear isomorphisms from U to U prime. We call them alpha, beta, gamma. Okay, such if you form this tensor product. Okay, so I want to avoid using lots of coordinates, so I write it this way. I apply it to T, I get T prime. So that's a nice definition. It gives an equivalence relation. Then there is very important the notion of direct sum. I think it was not explicitly defined so far. Also, I don't want to give the formal definition, but basically it's that if you have matrices, we know what is the direct sum of matrices, right? So. And you just do the same, play the same game in 3 dimensions. It's harder to draw. So this will be here, okay? Okay. And very, very important, we not only have direct sum, we also have tensor product. So and the tensor product is the tensor product. Okay, I could write it in coordinates, but I will not. I mean, it's the tensor product, and it lies here. And the only thing that I actually do is, okay, I write the space in this order, and I think of parentheses here, so that this becomes a tensor of order 3. This is my definition of the tensor product. Okay. So my goal is I want to explain there's actually a ring structure here. So it's a really nice algebra. So we also have a unit tensor, something like 1, which I denote with 1 with this brackets here. So this is a tensor in F, tensor F, tensor F. It's just 1, right? And it really has this function of a 1. So for instance, what I can do, if R is a natural number, okay, R is a natural number, I define R in these brackets. It's just a direct sum of R copies of the unit tensor. Okay, so this is they are also called unit tensors. I mean, they are, it's like generalizes the notion of unit matrix. Good. So, and what is important, maybe I should use some color. And now these isomorphism classes of tensors, they form a commutative ring. So isomorphism classes form commutative ring. because the direct sum is the addition, the tensor product is the multiplication, and you also have a multiplicative unit. So this is, I think, very important to have this clearly in your head when you make proofs, so you get a very clean way of writing down things. Okay, so this is the commutative ring, but that's not only that. We can also compare tensors. There's the notion of the restriction that JM introduced. So what is the restriction? So this gives an order. Restriction, I think everybody can see. Let's say t less than or equal t prime. And how do I define it? Okay, actually, I just realized I forgot something. I should have said here that alpha, when I defined isomorphism, I should have said alpha, beta, and gamma are isomorphisms. Probably I said it.
Are you insisting on concise tensors?
No, but I don't want to make it.
Then you can't insist on isomorphism.
No.
Just linear maps.
No. My definition of isomorphism is like that. I can do that. I mean, if I... it's an equivalent.
Put T in a larger space and make it not...
Then it will be not isomorphic.
It's not isomorphic to itself.
It's true. It's okay. Okay, but let's not talk about this. But what I wanted to say, when I do restriction, I exactly use this. I forget alpha, beta, gamma are not required to be isomorphism. These are just linear maps. But then otherwise it's the same. Yes?
I have a really stupid question. I'm sorry. The ring structure to the direct sum, the direct sum and the tensor product are the operations. Do they give you things of the same size? I think of a tensor product as being the product of the dimensions and the direct sum as being the sum of the dimensions. So obviously I've got it wrong.
Okay.
That's where you have to allow non-concise
Right.
tensors.
Okay, then correction. A little correction. Okay, I wanted to make this as simple as possible, but now the correction is maybe okay, let's say you have a tensor which is concise. So it's here, t is contained here, and you can't make u and v, w smaller. Then we say the tensor is concise, okay? But if you have a concise tensor, it's like in his home, there's no space, but sometimes you want to enlarge it, like by adding zeros, okay?
Yeah.
We can also allow that. Strassen called that equivalence, and it's actually the proper way of thinking about this is about the equivalence classes. But in the end, it's the same ring.
Okay.
It's the same ring.
Okay.
But then you have more freedom in regard to the dimension. You add zeros and then... Okay. Sorry for that.
Okay,
Yep.
thank you.
Okay.
Thank you. That
I
helps.
can ask quickly, just the statement that the isomorphism classes are a commutative ring. What's the product?
Tensor product.
Oh!
The tensor product is the multiplication. And this is exactly the thing. If you have t less than or equal t prime and t prime, okay, the thing is this. If you have this and this, okay, it's not true that you can, this would be wrong, okay, but it becomes correct, it's true when you're allowed to add these zero spaces, okay. I wanted to save some time, but then I lost time actually. But what is, as usual?
It's a semi-ring also, Peter.
Huh?
Instead of ring, it's a semi-ring.
You are right.
Oh.
Commutative semi-ring.
Yeah.
This is
no-
true
there's no-
because you don't have
Can't
minus.
subtract.
If you don't have minus. Thank you. Okay, I just wanted to test whether my audience is attentive. So it is. It's a semi-ring because you don't have minus. You have plus.
Is the tensor just the number one?
It's the number one. It's the number one in this. Okay. Okay. What is important that this restriction is transitive, which is trivial.
Is there a darker pen?
Oh yeah, we should get it.
Yeah,
You have a
probably.
whole bunch on the other
So many.
thing right there.
Okay, maybe there's even a black one. Thank you. Thank you. Yeah, it's transitive. It's transitive. So it's very important you... Okay. It's not great. Blackboards are nice, right? This one. Algebra press. So it's transitive. So this is how I compare. Okay. Okay. So I have this transitive order, and now when I have this framework, it's very natural that one can define tensor rank. We know what it is already, but let me repeat the definition. Now the rank of the tensor T, just the minimal natural number R in N, such that T is less than or equal to R's unit tensor. We had this on the board already, right? So, but what is important when that we can compare when you compare things, you do not just want to compare it by the rank, This is a bit stupid. It's like everything has a cost, like $5, $10, but you want to compare things directly. And for this purpose, you have the restriction. That's very important. Okay, good. So, we discussed this at length, that this tensor rank has a meaning in the world of computational complexity. It measures up to a factor of 2 the multiplicative complexity of the map. So maybe I should also write this. So like if we have, maybe I don't write it because we discussed it at length. So it's not just a mathematical notion, it's very relevant in computational complexity. And what I forgot to say, but I say now, this partial order is compatible with the multiplication and the addition, like in algebra. And it's very easy to prove. And from this, it follows that the rank is sub-additive and sub-multiplicative. So you have this, and you have this. Okay, sub. Okay. So now let's move on to the matrix multiplication tensor, like 2. I just write it, matrix multiplication, make it short. So I need to introduce a notation, so everybody uses his own notation. So I use the notation that Strassen used. So I have 3 natural numbers, E, H, and L. Okay, this tensor lies here. So I think this is a format that we should remember. It's very important. Maybe I should have written it in red, but now it's too late. So, what is it?
Maybe tensor product?
Yes, I write tensor product, yes. Sure. So what I'm thinking of this bilinear map, I multiply a matrix of format E times H with a matrix of format H times L. This is matrix multiplication. I get a matrix of this dimension format. This is the matrix multiplication. Now if you view this using some multilinear algebra, view it as a tensor, then you get this object. And you notice E and L are interchanged. It's kind of because you go to the dual. Okay, I could also write it in coordinates, but I will not do it. This is the tensor of matrix multiplication. Okay, and it has nice symmetry properties. So, if you look at this, you have 3 spaces. You can permute them, right? Now, if you do a cyclic permutation here, then what do you get? So, I have my tensor. And now, I do a cyclic permutation of these spaces, and then if you look at it closely, then you see it leads to a cyclic permutation of these coordinates. You can do it another time. L, E, H. The point is this. The tensor rank here clearly is invariant under permutation of these 3 coordinate spaces. Because for this reason, the tensor rank, all these 3 tensors, they have the same rank. So this is nice. They have the same rank. Same rank. Okay, so when I do cyclic permutations. Okay, so yesterday Olga explained that she revisited Strassen's algorithm. So let me recap what she did using this language, because then long arguments become very, very short and condensed, and this is very important for going on with the laser method. So now we have the 2 by, So this symbol here, 2, 2, 2, is my name for 2 by 2 matrix multiplication tensor. It's all about understanding this tensor and its powers. Okay? It's all about this single object. And Strassen discovered that the rank of this is not 8, is less than 8, is at most 7. We know it's 7, right? Okay? And now, how do you get this? Is of course Strassen. Let me write it for the sake of completeness. It was published 1960. Now, by the way, it was discovered in Berkeley, interestingly. And then what you do, you go to tensor power. So this idea of the recursive subdivision of the matrices is captured in the algebra using the tensor product. So what you do is this. Now I look at the multiplication of tensors of size 2 to the n. There is something that I forgot to write. Very important. Okay, something very important. Okay, let me write it here. Very important, sorry. Okay. So it's a very important thing. So if I have two tensors of matrix multiplication, this one and this one, tensor them, I again get the tensor of matrix multiplication. So this collection of matrix multiplication tensors is closed under tensoring. I mean, that is to say, these isomorphism classes. So this is the same as this. So you just multiply E with E prime, H with H prime, L with L prime. And this is very easy to prove. All of these things, you can prove it by writing the coordinates, the indices, but if you know the tensor product abstractly, it's clear. Very important. Okay, so this I will use all the time. Okay, if I apply this here, then I see this is the same as the 2, 2, 2 tensor raised to the nth tensor power. Now I take rank. They have the same rank, so this is an equality. The rank is submultiplicative.
Less than or equal to.
Huh?
Less than or equal to.
No. No, it's still equality. This is because now it's submultiplicative. Okay, this time I was right.
I didn't see where you put your phone.
Okay, that's okay. They have this. You see, but it's a clean argument. It's a very clean argument. And yeah, this you can write if you want is 2 to the n to the logarithm of 7 to the base 2, and this is this 2.81. So this shows that almost shows that this exponent of matrix multiplication is at most that. So maybe I don't have to write again the definition of the matrix multiplication exponent. We had it many times. So this shows, this implies this exponent of matrix multiplication, actually which depends on the field, is at most this. Or I can write it this way. 2 to the omega is at most 7. Okay, and what the point is, this argument has nothing to do with the fact that this is 2. I can replace 2 by h, and it's the same thing. So now I have multiplication of matrices of size h. Let's say the rank of it is at most r. Then by exactly the same argument, you infer h to the omega is at most r. So this is okay. Okay. And then we can go on with this game. So as you know, I mean, we don't even know the rank of 3 by 3 multiplication. We know nothing about this thing. I mean, we have estimates. It's very complicated, and that's why we focus on asymptotics, right? Because the hope is we can understand it better then. But another idea was not just to look at this multiplication of, not just to look at the cubic tensors, matrix multiplication tensors, but also multiplication of rectangular matrices, okay? And then, then there's another nice property, namely, for non-cubic tensors, I claim the following. I can generalize this implication as follows. Now I have AHL, rank of this is at most R, and I claim that this implies E times H times L to the omega third is at most R. Okay? Let me give the proof. It's a one-line proof. Okay? What is the proof? Well, I said if I do these cyclic permutations here, the rank is unchanged. So down here, maybe let me prove here. So I just write this again in cyclic permutations. Okay, all these three guys, they have rank at most R. Now, if I multiply, okay, means tensor product, these three things, I use this rule, then I get a cubic tensor. I get AHL, 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 right? And then I use that the rank is submultiplicative, so this is at most R cubed. And then I apply this rule, right? Then apply this rule, infer this. And I have proved this.
R cubed.
Cubed, thank you. Okay, so this is pretty simple. Okay, now, good. Now we move on to, to the, okay, Schoenhagen's tau theorem. I prefer to call it asymptotic sum inequality. I think it's nicer. What is this? It is this statement here. When you replace this matrix multiplication tensor by a direct sum of matrix multiplication tensors. Maybe I can write it here. Okay. I think this you can still read, okay? Up to maybe here. So this is the theorem by Schoenhagen. It's very, very important, really. It was this result that moved on the field a lot. So this, it says this. Now I have a direct sum. Let's say I have S many tensors, matrix multiplication tensors. I always write it this way. Let's assume the rank is at most R. Later on we will see if I have border rank, I can make the same conclusion, but let me first do it for the rank. Statement is, if I have this, then sum EI, HI, LI to the omega third is at most R. So it's a generalization of this. Now, if you look at it, think a little bit, then you realize if the rank were additive, then this would be trivial. Okay? But the point is, well, okay, the rank is not additive. That is not easy to prove. But Schoenhagen, when he proved the theorem, he also did it for the border rank, and in the same paper he proved that the border rank is not additive. So the point is, how can we prove this when we don't know this additivity? Okay, and now I try to give the proof. Okay, hopefully we eat up some of my time, but I think it's so important. Oops, it's worthwhile doing it. So,
Excuse me, just a question.
Yes.
So you said rank is not additive, but over here you wrote that it's
Sub-additive.
Okay.
Sub-additive.
So you need additive instead of.
No. I said if it were additive, then this would be immediate. But it is not additive, but it's it was open for decades before somebody, what is the guy, Shitov proved this.
And finally now there is a complete proof.
There may be a problem.
Not by him,
Yeah, there was a problem.
but
Yeah, but you see, it's difficult.
but this is like a month or two ago
Yeah.
that there was finally presumably complete proof.
Yeah.
You said that was a proof of the fact that this was additive, or?
No, the proof that it is that it can be strictly sub-additive.
Okay.
Okay.
And that was only that was asserted about 5 years ago, and there was a proof published, but there were some gaps that were fixable, and they finally got fixed.
Okay. So let me go on. If, yeah.
You covered and someone.
Okay, for proving this, let me first state the lemma, so then it will be smooth. And this lemma shows that it is extremely useful to have this notion of restriction. So what I have? N, I call it now N, is an integer tensor, a tensor T. Let's assume this is at most R. Okay, so this just means T plus T plus T plus T, N additions, direct sums, right? N times T is T plus T plus T plus, okay? So the rank is at most R. And then what let's assume, okay, let's assume the rank of T prime is at most N. Okay, and I claim then the rank of T prime times T is at most R. I give the proof. The proof is very short when you have this notion of restriction, otherwise it wouldn't be so clear. The point is use restriction. I just rewrite this. I say that the rank of this tensor is at most R, means that this is a restriction of the R's unit tensor. This is just a rewriting. And now you see, and this means T prime is less than or equal this. And I said the restriction is compatible with this tensor multiplication. So therefore, it's like in algebra, right? This is less than or equal n times. Okay, sorry, I think. Okay, I got it wrong. Okay. Like, and is the, okay, how do I mix it? What do I do? And T. Did I do everything? It's okay. It's correct. And then I say this is this. Okay. And that's it. So it's very elegant. And without the restriction, you know, that's why restriction is actually we shouldn't even write rank, but you just use restriction. Okay, now the proof of the theorem. Okay, so it's okay. So what do we do? Okay, I have my tensor here, direct sum of matrix multiplication tensors, and I take an nth tensor power. And I use the multinomial theorem. Okay, it's the binomial theorem, the multinomial theorem. It holds in any commutative ring. But as I said, I have a commutative ring. I could just do it. So it's the multinomial theorem. I use it. So, you know, it would be more elegant to write just plus and times. But somehow I feel maybe I should not do it here, otherwise, okay. But basically, that's the way I think about it. Okay, so nth thing. And then this is, let's say, isomorphic. And then I have this big sum. It's a direct sum. Okay, so it's like in combinatorics. So I sum over all distributions, mu in n to the s. The sum of the elements of mu is capital N. And then I have this multinomial coefficient, n over mu. That's a natural number. But, you know, let me put this thing here, just saying, actually I interpret it in my ring. And then I have this tensor product. What do I have? You see, it's important that it is commutative, of course. Otherwise, it couldn't do this. It's the multinomial theorem. Okay, this is the multinomial coefficient. Okay, it's important in what follows. Okay, so, but now, so this, how about this thing has rank, the whole thing has the rank at most r to the n. Okay, so now I just focus, maybe color, on that. I fix some mu then I look at this tensor. Then, of course, this tensor also has rank at most r to the n. And what I want to do, I would like to apply this principle, but there is a problem, because here is just one matrix multiplication tensor, but here I have a direct sum of many of those. So the idea is, okay, I think in terms of restriction, I have this thing, this integer, and I make it smaller, right? So I make it smaller, and I replace this by a cubic matrix multiplication tensor, just in my mind, okay? And this I do using the definition of the exponent. So I think I should erase a little bit. Here. Okay. Okay. Not perfect, but okay. Okay, so now question is, should I write epsilons or not? But in the end I said yes, because it's nice to see, well, that how constants, constants are very important when you do practice, of course, but for this asymptotic theory, constants are irrelevant, okay? And I will show you how they disappear. And so for this reason, I fix some epsilon. Then I say there is some constant. Maybe a billion, who knows, doesn't matter. Such that for all n, now what I rewrite is basically the definition of the exponent of matrix multiplication. So the rank of the NNN tensor is at most is constant, n to the, here have omega plus epsilon. Because the omega is defined as an infimum, so okay, this is the definition of the exponent. Okay, looks like calculus. So now I define, what do I do? Okay, let's define the natural number m. I have fixed some mu. I take the multinomial coefficient. Now I raise it to the power 1 over omega plus epsilon. Of course, I should do some rounding, so it should be a natural number, but let's not mess it up, okay? So this is, think of an integer. Now what do I do? So, okay. So what did I say? I said this has rank at most r to the n. So let me rewrite it. Okay. Okay, so this is... It requires some notation. So the rank of this is at most r to the n. Now, now let's squeeze in here this constant c epsilon, here and here, then it will still be true. Okay, now what can I do? Right. So, okay, maybe this was not very clever. Let's write this in a more. It should be clear that this is a matrix multiplication tensor. I can write it this way, where E mu is just this. It's a monomial, right? And the same with H mu and L mu. So these are these monomials, and this is just this. Now, as I said, now I can make this smaller. Like I replace it using this definition, and what I get is this. Maybe there are too many technical details here, but I try it anyway. So I claim I get this. Rank is at most. Okay. Because I'm wondering, yes. I use this, okay, I replace n by this m. Is it correct? I have on the right-hand side. Yes. Huh? Yes, I'm just thinking
Over here is a matrix multiplication.
Yes, so you see, because the point is m to the omega plus epsilon is this thing. So I have this. It's
Why did it get converted to a matrix multiplication?
He's using restriction.
yeah, I'm not. Yeah, I used restriction, and this I by this property that I still here.
Yeah.
Now I can. You see, it's. So this is a matrix multiplication tensor. Okay, so then I can apply my principle. So because I know already this theorem is true when s equals 1. Okay, then what do I get? M to the omega. Omega to the third. And then, okay, from now on, okay. Okay. So now how to continue? Now, what we can do now is, like this holds for any mu. Okay. So what I can do now, I can multiply, I can add over all distributions, and I again apply the multinomial theory, but this time in the integers. Okay. So, and right. So what do I do? Okay, there is a little thing. This is, you see, okay, now this is technical. Actually, I have to multiply. Here, let's multiply with m to the epsilon. Then I can put here an epsilon. And then I get here the multinomial coefficient, right? And then I sum over all mu on both sides. And what I get here by applying the multinomial coefficient is this. Now this is important. Now I have this. Omega third. Oh, I'm skipping a little step, but it's not. Okay, this is this. Okay. Are you still with me, or? Okay, I know it's after lunch. Just the multinomial coefficient, multinomial theorem. And here, the point is I want to take the nth root, let n go to infinity, and then see lots of ugly terms disappear. Okay, there is a little bit of, okay, so now here. How many of these distributions I have? At most n plus 1, no, to the s, right? This is the number of mu's that I have. And what else do I have? M to the epsilon. There's this c epsilon nobody cares about, and this. Now let's take nth roots. Okay, maybe in color. Let's speed up this a little bit. Okay. S. So now I take nth root. Then here is n. This goes away. Here is 1 over n. And then if I let n go to infinity, what I get is this. Is at most, and you see what is important. We know the nth root of n goes to 1 when n goes to infinity. So this will go to 1. This also converges to 1. So the only thing that remains is this m to the epsilon. And then here I have r. But then epsilon was arbitrary. So, and let it go to 0. So this will disappear. And I get this. But that's the proof. That's all. This is the Schoenhagen-Tau theorem. Okay? It's a bit technical to write, but I thought still to do it with the epsilon, then you see how the constants disappear in the asymptotics. And this idea reappears many, many times. When you do this theorem, you do this such argument all the time. Okay, so, okay. Now, don't have much time. So the thing is, this also is true when you replace rank by border rank. Now, I rely on JM, who introduced the border rank. I'm not, okay, I don't have time to repeat the definition. And, okay, now you need a little argument, you need an additional argument. Let me, okay, we had, what was the argument? So there is some proposition which I don't have the time to prove, but it's not very difficult. So if the border rank of a tensor is at most R, and this is of order Q, unfortunately I think it was not defined, means approximation in terms of epsilon of order Q. I don't have time to explain, but then by an interpolation idea, you can prove R of T is at most 2Q plus 1R. It's not difficult to prove. Okay, but you need to have the right definition of border rank. I should say border rank, Joseph defined it in terms of closure of orbits. It's more a topological definition, but if you want to prove this, you should have the algebraic definition when you go along a curve. You gave even better, okay? But now exercise is for you. Now, if you believe this proposition, just revisit the proof of the Schoenhage theorem and show that it's still true for this bar. So this proposition allows you to show that it's also true for border rank. Okay. So, good. Now, and there is this Schoenhage example. Okay.
You also need to know how the order changes under chronic
Sorry?
power. You also need to know how the order changes under chronic power.
Excuse me?
In order to do that, you also need to know how the order grows.
Yeah, you have to write. You have to write. If you go to the nth tensor power, then yes, you need this. Okay, for those who want to solve the exercise, this is the sub-multiplicativity of the border rank, but you need of order, but then it only grows linearly. This is the thing that you have to exploit. Okay. So now this famous example by Schoenhage. So let me write it. Which shows that the border rank is not additive. So Schoenhage's example. It was in the same paper. Okay, now this is very interesting. So let me explain. So, okay, I use this notation. Maybe you find it a little bit cryptic. Okay, so I look at this tensor. It's a matrix multiplication tensor. But what is it? It's this. It encodes this map. This multiplication. So this is like the multiplication of a column with the row. Joseph had it, I think. And then, you know, the rank of this, the upper bound EL is obvious and the lower bound falls by conciseness. But this is very simple. How about this? 1, M1. This is an inner product. It's the inner product. Also a matrix multiplication. Clearly, the rank of this is M. Okay. Now we do the following. Now we take a direct sum of two of these guys. I take this, direct sum, this, and I take for M, I take this number, E minus 1 times L minus 1. Okay? So border rank. Okay? And the amazing statement is, now, is this equals EL plus 1. This is the dimension.
You might want to say also the border ranks of those two are.
Oh, yeah, right.
Yeah.
Yeah, thanks. It was not wrong what I said, but now it matches
It was
more
not
nicely. More nicely. Okay, but you see, the trivial upper bound would have been EL plus M. So this is the M. But here is just a 1. So people express this, they called this disjoint matrix multiplication. Like you have this operation, and now you say, if I want to do both simultaneously, then you kind of can mix Okay, the data somehow do some clever bilinear algorithm approximative, you have this. So this is, wow. Actually, you can write the proof. The proof of this is some identity using polynomials that you can write down in a few lines, and you can verify it, okay? Understanding it is another issue. I don't think, okay, Joseph has some geometric understanding of this, right? I think there's some kind of magic here for me still, okay? Good.
Could you say why polynomial identity would give you a key to this observation?
Yeah, why? Because, right, then good. Okay, the polynomial identity is, then I would need to recall on that, maybe I even have a little bit of time. What does it mean that the border rank of a tensor is less than or equal to R? I can express it, okay. I can express it this way, actually, for two things. Joseph introduced also the notion of degeneration. So let me just write this. So it will be just a tautology. So there is a way of defining this degeneration. I don't have time to do it. It's like an approximate version of restriction, which allows, okay, to express it this way. Okay, so I just introduced this notation, but now I tell you what this means. Okay, there are many equivalent definitions, but it means there is some natural number q, and there is some tensor t prime, but this tensor is defined not over the base field, but, okay, here is my base field. Now I take the polynomial ring over f in some variable epsilon. Epsilon is a variable, right? It's not even a field, it's a polynomial ring. So think of a coordinate tensors, right? All the entries of t prime lie here. And then I say epsilon to the qt plus some tensor t prime, no, epsilon q plus 1, some tensor t prime, which is also defined. Okay, yeah, I just wrote it. I compare this with the rth unit tensor. I know this is made heavy to digest. Here I want to put restriction. But now this restriction should be defined. And if you remember, I defined restriction in terms of these linear maps alpha, beta, gamma. They were over the field. Now alpha, beta, gamma are over the polynomial ring f epsilon. Okay, everything. There is no division here. There are other ways of writing this, but now this is like a division-free thing. That's why I have to work over the ring. So you see, the point is, this is like t plus like a little perturbation, okay, times epsilon q. And this thing has rank at most r. Now, if this were not here, if q were 0, I can let epsilon go to 0, and then I have restriction. But if q is greater than 0, I can't do this, right? I can't do this. So this is why I get a new notion. Now you see, okay, now instead of tensors, if you want to write down these things, it's actually more convenient to write trilinear forms, like you have x, y, z's. And then you write this identity. I mean, this is this means this is like alpha tensor beta tensor gamma r. And just write this down, this identity, and verify it's true. Okay. Okay. So, good. Now let's move on. So this was, okay, no, I had to say Schönhage. Okay, maybe to finish this up. Of course, if you have this, okay, then I can apply, the point is, of course, to apply this inequality. So this, okay, I call it asymptotic sum inequality, okay. If I apply it, what do I get? EL to the omega third plus this, the omega third is less than EL plus 1. Now this is an inequality and gives you bounds on omega, right? So now the question is, what are the best E and L? And if you do the numerics, you see, okay, I continue here. So if E and L are 4, then it gives you, what do I have? I continue here, I have 16 to omega third plus 9 to the omega third is at most 17, and this gives you an upper bound, which is 2.55. So this is due to Schönhagen. Now you see, okay, this proves omega is less than 2.55. This is the method. Okay?
And this is just coming from something about an outer product direct sum with an inner product.
Yes. And you see, this thing is composed of like 2 matrix multiplications and, well, in a way a bit trivial, like they are like flat, you know, but they are put together in some way. Okay, now next, okay, this was like my introduction. Now the goal is to explain the laser method. The laser method tries to generalize this idea. This is like one example, but can we make this idea work in larger generality, right? The answer is yes. And so, okay.
Can I ask a quick question here? So
Yes.
just for context, like, once you've proven that omega is bounded in this way, is it obvious what the algorithm is? How do you generate the algorithm? Or is that not?
Okay. The algorithm is a bit hidden in, I mean, look, Olga, she took 45 minutes and so to explain the algorithm.
Yeah, but she had, like, her starting place was a fast algorithm.
Yeah, but the point was really rank of 222 is less than or equals 7. Okay, and if you unfold it, it's not so easy, right? That's, I mean, if you unfold this, you can unfold it, but it will be complicated. So I ignore all this unfolding because I want to just bound this exponent.
In particular, you have to pick an epsilon.
Yeah.
Because it's a finite, you can't take the limit as n goes to infinity.
Yeah.
And then that epsilon will tell you what n you can get within. So you may need a very, very large n.
So you can use this, you would construct an algorithm for like n to the 5.
Sorry?
Never mind, I think I understand.
I don't know what would be the
You need
constants. Yeah.
You need an enormous matrix multiplication to make
Yeah.
this work. Like really, really big.
I never tried to figure this out. I mean, I do not know how big it will be.
Well, but for the other one, it is figured out in its number of atoms in the universe.
For which one? For?
Coppersmith-Winograd.
Oh, yeah. Well, you're not there yet.
I know, but I'm just saying that it's probably not so far from that.
Okay, so next topic is called combinatorial degeneration. Okay, well, there's some combinatorics here. So what do I do? So the idea is I have a tensor, and I want to do a block decomposition, like with matrices. And there will be an outer and an inner structure, right? And the inner structure should be, should be all matrix multiplication tensors. The outer structure will be something else, but I try to deform or degenerate the outer structure to a diagonal tensor. Okay, so that's a bit rough, but so now, okay, because I want to write these statements, again, there will be some notation necessary. So the following I call a decomposition. So I have my tensor T in U tensor, V tensor, W. And what I do, I assume I have direct decompositions of all 3 spaces. So I have a finite index set I here. This decomposes U. I decompose this, V. Index set J. And then maybe I put it here, W over K. So I have this. And then the idea is, okay, I don't want to draw it 3-dimensional, but I have 2-dimensional thing, block decomposition, right? And then my tensor T, which lives here, okay, has, you have, in all of these blocks, you have something So you can actually write T as a sum of Tijk. Okay, this is in this index set. This is like a combinatorial cube. And the Tijk, I can think of lying here in this tensor product. Okay, I mean, actually, I enlarge these spaces, but you know. Okay, I hope you understand. Now, okay, these things I call the decomponents. Okay, this is what inside here. And then for the outer structure, I'm interested in the so-called support, the D support. So this just tells me in which blocks I have something non-zero. So I don't know, maybe it looks, maybe, I don't know. Maybe here is nothing to make it a bit interesting. Maybe it looks, but it should be in 3 dimensions. Okay. Now, the point is, okay, I want to deform this outer thing to a diagonal tensor. But okay, what does this mean? Okay, now let me give a definition. Okay, so definition. I define combinatorial degeneration. So now this is actually just combinatorics, but inspired by invariant theory. So I have I times j times k. This is a combinatorial cube. Inside, I assume I have a set phi. Think of phi is the support. Phi, this could be phi in my application. It's the support. Okay, and I want to make the support smaller. You know, I want to get rid of certain stuff because in the end I want something diagonal. So I have a psi here, subset of phi, and I say psi is called degeneration, combinatorial degeneration of phi if and only if. Okay, now comes the definition. So, well, notation. Good to have a notation. I also use this notation. If there are maps, A goes from I to the integers, B from j to the integers, C from k to the integers, such that, okay, you look at this, AI plus BJ plus CK, then you want this to be 0 if ijk is in the small set, in psi. And if you are outside, okay, if this is in phi but not in psi, you want it to be positive. And if ijk is outside of the phi, you don't care. Okay? And why is this interesting? Because of this proposition, which says this. Now I have a combinatorial degeneration. Okay, I'm in this setting. I have a decomposition D of a tensor T. Okay, psi is a combinatorial degeneration of the D support, of this support. Then, so this is a combinatorial thing, right? But then I can infer something interesting. I can say, let's look at the tensor, which here, okay, this sum actually was over the support, right? Because when there is 0, I don't have to put anything. But now I can replace the support by psi. So it's smaller. And this should be a generation in the sense, well, this sense here, of T. In particular, the border rank of this is at most the border rank of T. Now, okay, I understand. Writing this proof would maybe take 5 minutes, but I want to save time for other things. It's not difficult. Okay, because you would, yeah, I can say, what would you do? What would do, okay, maybe I give you the idea. What would be the linear map alpha? Just give the proof idea. I have a vector here in U. Now, okay. And I would define it this way. So this, the UI gets scaled with epsilon to the AI. So you see now this is a linear map, but it's now defined over this polynomial ring. Actually, it's not the polynomial ring because it can be negative here. Let's say field of fractions. Okay, you can have division by epsilon. You do it the same with the B and the C, and then you apply the tensor product to that, and then you look what happens. And then you see the positions where you have psi, you have in the exponent epsilon to the which is 0. It's there. Okay, you can forget about it. While outside you have something positive. And then you are in basically this setting. So, okay, I'm a bit vague, but it's not a difficult proof.
Geometric formulation.
Huh?
You're defining a torus, actually.
That's right. So the people that are more into algebraic geometry would say, yeah, you go along a one-parameter subgroup in a maximal torus. But these are all words, but that's what it is, right? Okay, what is the strategy? Okay, maybe good. I can finish the strategy, and then we can have the break. Yeah, but if you give me 2 minutes, I can. Yeah, sure. But this is okay. Let me give one definition, and then we can go into the break. So I didn't say, I said it, but I didn't write it. This psi should be, so that would be a diagonal. Okay, what is a diagonal? Call psi, subset of this, diagonal. If the projections onto the coordinates are injective, so the projections, okay, you can projections. So I hope you understand. Here is a projection like P sub I. Just ijk is mapped to I, and I have all 3 projections. Okay, sorry. If are injective. You want these projections. Now it's something like in 2 dimensions, something like that. Maybe not full, right? Something. Of course, you can have permutations, but in 3 dimensions, like 3-dimensional partial matching thing. This is diagonal. Now one observation is this. Now if psi is a diagonal, then this sum over psi, which we get here, will become a direct sum. You see? And then we are in good shape. Then we can apply the Schönhage if these Tijk are all matrix multiplication tensors. So this is the strategy, somehow, to come up with such a setting here. Big tensor, decomposition. It has a support. From this support, you want to degenerate to a large diagonal. From the big tensor, all the parts, components should be matrix multiplication. And of course, you should have a good upper bound on the big tensor. So in order to have good results, the big tensor, experience shows it should be a tensor of minimal border rank. Well, then you have the best results. So this is the plan. Okay, and then after the break, I tell you how to implement this. More details. Okay, thank you.
Any questions? Yes, we'll take them again and then.
It was all clear, or maybe it was after lunch. Thank you.